Hello, discrete math fans. We're going to revisit the binomial theorem. We talked about this earlier in this section. The binomial theorem says that for any complex numbers a and b, and any whole number n, a plus b to the n can be written as a sum of monomials. The sum, where k goes from 0 to n, of n choose k times a to the n minus k b to the k. Now it's possible to prove this algebraically, but it's really messy and it's not very illuminating. Now if you're interested in seeing it, I've included a proof of this in the additional notes document. Instead, let's work out a combinatorial proof. And as I've discussed many times in this section, combinatorial proofs are better anyway. We're going to give two different proofs. Here's the first one. Now when we multiply out a plus b to the nth power, the way that we get a term of the form a to the n minus k b to the k is by choosing a b term from k of the a plus b factors. The rest of them will be a. Now they're going to be n total factors. How many ways can this be done? Well, there's n factors total. We'll choose k of them, so this can be done in n choose k ways. And that tells us that a plus b to the nth power is equal to the sum that we want. All right, I'm going to give you another proof. This is going to rely on the theorem that says that if you have two polynomials of degree n and they agree on at least n plus 1 inputs, then the polynomials are equal. All right, so let's choose a and b to be natural numbers instead of complex numbers. We'll create a combinatorial interpretation of the two sides of the equation. So let's pose this question. In a class of n students, each student is given the choice of solving either an algebra problem or a geometry problem. There are A, algebra problems, and B, geometry problems. How many different outcomes are possible? Well, the first answer is very easy. There's simply a plus b to the nth power different possible outcomes, because each student has a plus b different choices that they could make, and so we'll just multiply that out n times. Now in our second answer, let's let k be the number of students who decide to solve a geometry problem, and so k could range anywhere from 0 to n. Now there are n choose k ways to determine which k students decide to do a geometry problem. There are b different geometry problems and k different students doing those problems. That means there's b to the k ways for those students to select problems. And similarly, there's a to the n minus k ways for the remaining students to choose an algebra problem. That means we can say that when k students decide to do a geometry problem, there is a total of n choose k times a to the n minus k b to the k ways for all of the students to choose a problem to do. Then we sum over all possible values of k, and we get the expression that appears on the right-hand side of the binomial theorem. Therefore, we can say that a plus b to the nth power is equal to the sum. K goes from 0 to n choose k, a to the n minus k, b to the k. Keep in mind, though, that in this proof, we said that a and b were natural numbers. But we can note that for any fixed value of b, both sides of the equation are a degree n polynomial in a, and they agree on an infinite number of points, and therefore they must be equal. That means we can go ahead and substitute in complex values for a and b, and we'll have still proven the binomial theorem. Okay, that's all for now.